Welcome to Easy BTech, your guide for BTech and beyond. In this channel, you can learn the subject very easily. My name is G. Sampath. I am going to explain the subject VLSI. Today, let us discuss about IDS versus VDS. IDS versus VDS relation. IDS versus VDS relation. It is a basic electrical relationship of MOS transistor. It is a basic electrical relationship electrical relationship of MOS transistor, MOS and BiCMOS circuits. BiCMOS circuit. Now, what is IDS? IDS is IDS is drain to source current. Drain to source current. VDS is VDS is drain to source voltage. Let us see this in a circuit symbol, then we can see in the figure representation. You can see this one. Let us take a NMOS transistor. Let us take NMOS transistor. If you are applying external voltage, VGS, if you are applying external voltage, this is a VGS. VGS we are applying, and the channel established, there is a current flow from drain to source. Drain to source, and this one is a VDD, drain terminal, and this is a ground terminal, VSS. You can say this is a gate terminal, drain terminal, and source terminal. These are the three terminal MOS transistor, NMOS transistor. This is NMOS transistor, NMOS transistor symbol, NMOS transistor. And we can take output voltage. We can take output voltage, or voltage here is called VDS. Now, when you are applying VGS voltage, channel established. There is a channel established. There is a channel established between drain and source. Channel established between drain and source. It may be the flow of charge carriers from here to here. We are seen in enhancement transistor. There are two conditions. One is non-saturated region, saturated region, and saturation region. There is a flat channel existed. Flat channel existed. Two conditions are here. Two conditions are here. So this one is called inclined channel existed. This one is called saturation region. The first one is non-saturated region, non-saturation region, inclined channel existed. Second one, saturation region, flat channel existed. Saturation region in this symbol representation. Let us see this one in figure representation. We have, let us take a NMOS transistor, NMOS transistor, an NMOS transistor. Source, SiO2 layer, drain, and polysilicon act as a gate. Now the top layer is metal layer, is a metal terminal for conduction from source to drain. Here we apply external battery voltage, and here we can take a source to drain terminal, source to drain terminal. And the figure layers representation in NMOS, we can take it is a p-type substrate area. This is a p-type substrate area, p-type substrate area, source and drain n plus diffusion, forward lines with the near distance representation, and this one is a metal layer. This is a metal layer. This is a metal layer. Here also top layer is metal layer, and this is below this SiO2 layer, dielectric layer from gate to channel, and this one is a polysilicon, backward slashes, nearer distance. So when you are applying VGS, this is a VGS. VGS is a positive voltage we are applying. Let us say if this is a logic 1 we are applying, logic 1 we are applying, the channel established, the path established here, the path established from drain to source by applying VGS. So VGS is positive in NMOS, positive or logic 1 volt, positive or logic 1 volt, logic 1 volt. So there is a charge established, field induced in this, you can see. So it is a positive terminal. All negative charge carriers are attracted to this positive terminal. Positives, negatives are separated. So without applying any voltage, there is no movement in this charge carriers. Polysilicon is metal, is also conduction layer. Positive and negative charge carriers are here. So in this also, by applying charge voltage, there is a movement in the charge carrier, positive negative charge carriers movement. So what happens here? All the negative charge carriers in the polysilicon will be attracted towards its positives, and positives over here, and SiO2 layer also negative charge carriers, negative charge carriers, and below SiO2 layer positive charge carriers are formed here. You see there is an electric charge, so positive negative, positive negative, positive negative, there is a charge induced from polysilicon to channel. You can say from the top layer metal to channel area. In the p-type, this is a p-type substrate area. So all positive charge carriers, negative charge carriers are here, positive and negative charge carriers are here. So whenever positive are majority, negative or minority charge carriers, whenever applying VGS, then some VT voltage is required to move these minority charge carriers towards this SiO2 layer. You see this one. So what happens? Minority charge carriers, negative electrons move towards the substrate area, form a channel between source to drain. So there is a channel established. Minority charge carrier move towards this SiO2 layer, and here is a charge form. Here is a charge form. the minimum voltage required, minority charge carriers move from here to the substrate area SiO2 layer. Minimum voltage is called threshold voltage, that is VT. Applied voltage VGS. The remaining voltage over here, the remaining voltage over here, the remaining voltage. So applied voltage is VGS, and minimum required voltage is VT. Then the remaining channel voltage is VGS minus VT. VGS minus VT. Now there is a channel formation. After that, there should be a current flow from drain to source. Current flow from drain to source, that is called IDS. IDS. We are applying voltage here, VDS. We are applying voltage VDS. So after formation of a channel between source and drain, so we need to apply a voltage over here VDS. Then all the negative charge carriers, this is a negative charge carriers, end diffusion, negative charge carriers attracted towards this positive plate, negative charge attracted towards this, and the current flow in this direction. Electrons are moving in this direction, current flow in this direction. So IDS, current IDS flow due to this VGS and VDS. VGS and VDS. So now IDS versus VDS current flow in these two conditions. First one is non-saturated region. Non-saturated region. Non-saturated region. In the non-saturated region, the condition is VGS minus VT. So applied voltage VGS, channel voltage minimum threshold voltage required VT, and then the channel voltage VGS minus VT less than VDS. Drain to source voltage is less than the VGS minus VT. So there is a current flow in this current flow in non-saturated region. IDS flow. And gate voltage VG is equal to VGS minus VT, and VT is the threshold voltage is average of drain to source voltage. This is the condition, and we can say charge induced, the IDS flow between drain to source, IDS flow, this current IDS flow in this because of the charge induced. So charge induced because of this electric field, gate to channel electric field, insulation medium, and there is an air gap between this source and drain. Now QC is a charge carriers. This will by the insulation material, charge carriers, insulation material, that is SiO2 layer, and epsilon naught is a free space permittivity, and area of the W into L, area of that polysilicon area, and EG is the gate to channel electric field. QC is nothing but QC is the here charge carriers, charge induced in the channel because of the electric field from gate to channel, and insulation medium SiO2 layer, and the air gap epsilon naught, and area of this one. So you can say this one, this is a width W, width of the polysilicon, and this is the length of the channel. W is the width of the polysilicon. Here W is the width of the polysilicon, L is the length of the channel. So let's write this one. EG is a average gate to channel electric field and epsilon insulation. It is SiO2 layer between the channel and the polysilicon. SiO2 layer, the value here 4.0, and epsilon naught. Epsilon naught is a free space. Free space happened when it is in moving magnetic charge towards this SiO2 layer. Free space. The value is 8.85 into 10 power minus 14 farads per centimeter, and W is the width of polysilicon. W is the width of polysilicon. L is the length of the channel between source and drain. L is the length of channel between source to drain terminal. So let us find out this. So before going to this non-saturated region, so we have IDS. IDS formula. IDS, we know that IDS is equal to QC by transit time between source and drain. So what is QC? QC is nothing but charge induced in the channel. Charge induced in the channel. Charge induced in the channel. And transit time, tau SD, is the transit time between source to drain. Now what is find out this transit time, then we can see the charge induced in non-saturation and saturation. So what is tau SD? Tau SD is defined length by velocity. So here L is the length of the channel. V is a velocity between source and drain. Velocity between source to drain. Let us see the velocity. V is equal to mu into EDS. Velocity formula, mu into EDS. So where mu is the mobility charge carriers. Mobility charge carriers, electrons and holes. Electrons in NMOS and holes in PMOS charge carriers moving from source to drain. EDS is the electric field between drain to source. Electric field between source to drain. So let us take this equation number 1. Let us take this equation number 1. IDS is equal to current flow from drain to source depend on the charge carriers from source to drain and time between source to drain. And tau SD, it is length by velocity, equation number 2. And V is equal to velocity, this V is equal to mu into EDS. Let us take equation number 3. Now what is EDS? Electric field EDS is equal to VDS by L. VDS is a drain to source voltage. VDS is a drain to source voltage. L is the length of the channel between source and drain. So let us take this is the equation number 4. Equation number 4. Now EDS substitute in this equation number 3. Equation 4. Substitute equation number 4. Substitute in equation 3. In equation 3. Now what happens? The third equation, velocity V is equal to, what happens? V is equal to mu into EDS means VDS by L. VDS by L. So EDS means VDS by L. EDS is substituted over here. Now let us take this the equation number 5. Now equation number 5, velocity V, substitute in equation 2. We have transit time is equal to length by velocity. Now length by velocity V is equal to, in previous, V is equal to mu into VDS by L. So substitute this mu into VDS by L. So this will become L square by mu VDS. L square by mu VDS. So what is this equation? Equation number 6. Take this equation number 6. So this is equation number 6. We have found this transit time between source and drain. Keep it in a box. We found this transit time. Now the another one is we need to find out this charge induced in the channel. So IDS drain to source current is equal to charge induced in the channel by transit time between source and drain. So we derive this transit time between source and drain. Let us find out the charge induced in the channel. Charge induced in the channel. Then substitute here. Then we find out the IDS in non-saturation and the saturation region. Now here IDS in non-saturation region. IDS in non-saturated region. So before that we have this QC, charge carriers. So QC is equal to charge induced in the channel. It will be depend on this average gate to channel electric field, epsilon insulation and epsilon naught W into L. So we can find out this EG. So EG is equal to gate to source voltage by length of the field. This will be equal to, we can write this, VG is nothing but VG is VGS minus VT minus VT is VDS by 2 and L is a length. So it is a thickness of the SiO2 layer. We can say this is a D. Now we can substitute this. In this QC. QC is equal to we can take this epsilon insulation, epsilon naught W into L, and this EG substitute over here. EG is average electric field, VGS minus VT minus VDS by 2. So divided by, you can take divided by D. So up to this is a QC value. Now write down the total equation. IDS is equal to IDS in non-saturation region. IDS is equal to QC by tau SD. So this will be equal to epsilon insulation epsilon naught W into L by D into VGS minus VT minus VDS by 2 VDS by 2 VDS by 2 and divided by, we have this transit time. Substitute this transit time also. So what is the transit time? We derive this L square by mu VDS. L square by mu VDS. So what happens is L and this L will be cancelled out. We can rewrite this equation: epsilon insulation epsilon naught. So mu is multiplying over here, mu into W by L, mu into W by L by D, and this VGS minus VT minus VDS by 2, and this VDS is multiplying over here. So what happens here? Mu into VDS. So mu will taken here. VDS is multiplying, and multiply take inside of this brackets. Now what happens here? Epsilon insulation epsilon naught mu by D into W by L VGS minus VT. We take VD inside, so VDS, and VDS is multiplied over here. It is VDS square by 2. So we can write IDS is equal to epsilon insulation epsilon naught mu by D. Let us take some constant K into W by L VGS minus VT into VDS minus VDS whole square by 2. Let us take, this is the equation number. So what is the equation number? Previously 6. Now equation number 7. So this is take equation number 7. Now IDS is equal to K into W by L. Let us take it is a beta. Now we can write the equation VGS minus VT into VDS minus VDS square by 2. This is a very important equation which will ask in the external examination. So definitely we can practice this equation. So it is equation number 8, beta. Now IDS can be taken. We have gate to channel capacitance. CG is equal to, we can write this epsilon insulation epsilon naught W into L by D. So parallel plates. So capacitance from gate to channel, polysilicon and the channel, parallel plates. So gate to channel capacitance, you can see the first we seen this polysilicon is a positive and charge carriers is a negative. So positive plate, negative plate, in between this SiO2 layer is there. This is a distance. This is the distance of this SiO2 layer. Now we can write the IDS equation. Instead of K, you can substitute this CG. So gate to CG is we can write this CG is nothing but gate to channel capacitance. gate to channel capacitance. So IDS can be right. Let us take this K is equal to K instead of this in terms of CG. So CG into mu by W into L. If you substitute this CG value over here, we'll get the same K value. So K is in terms of CG. CG into mu by W into L. So we can write IDS. So where K is, we have K into W by. Instead of this K, you can substitute in terms of CG. So CG into mu by W into L into W by L into W by L. The remaining equation will be same, VGS minus VT into VDS minus VDS square by 2. Now W will cancelled out. Then IDS in terms of CG into mu by L square and VGS minus VT. This is a current equation of in terms of gate to channel capacitance, VDS square by 2. Let us take this equation number. You can see what is the equation number 8. Now it is equation number 9. This is equation number 9. Now sometimes we can take CG is equal to, we call CG is equal to capacitance per unit area. If you take only polysilicon, then C naught into capacitance per unit area. This is called capacitance per unit area. Capacitance per unit area. Capacitance per unit area. So CG is equal to, CG becomes C naught into W into L. W is the width of the polysilicon, L is the length of the channel. Now what happens? This IDS will become, now this IDS become above equation 9 will become, in the place of CG you can substitute this C naught into W into L, then remaining mu by L square, this VGS minus VT into VDS minus VDS square by 2. Now L and this square will be cancelled. Then C naught into mu W by L. So this will be equation number 10. Equation number 10. So this is a non-saturation region. Non-saturation region, what happens? First we written this K. Let us take this in a box. We have taken this in box. So K into W by L, current equation in non-saturation, and this beta and this CG in terms of CG. You can take in terms of CG this value. Keep it in a box, and this one. So K into W by L, VGS minus VT into VDS minus VDS whole square by 2 in terms of gate to channel and gate capacitance per unit area. Let us take this one in saturation region. Let us take this one in saturation region. So in saturation region, second one is saturation region current flow. Saturation region current flow. VGS minus VT is equal to VDS. VGS minus VT, there is a flat channel existed between source and drain. Then in the equations we have IDS is equal to non-saturation. IDS is equal to K into W by L, VGS minus VT VGS minus VT into VDS minus VDS whole square by 2. So this is the equation we already written in non-saturation region. So K into WL, equation number 7. This is equation number 7. Equation number 7. Now equation number 7 becomes equation number 7 becomes where VDS equal to, substitute this VDS is equal to VGS minus VT. VGS minus VT. Now then saturation region IDS is equal to K into W by L. Substitute this in place of this VDS, VGS minus VT. So channel voltage is equal to the drain to source voltage. So VGS minus VT into VGS minus VT minus VDS means VGS minus VT whole square. VGS minus VT whole square by 2. So simplifying, and we'll get K into, so VGS minus VT into VGS minus VT. What happens is VGS minus VT whole square by 2 minus VGS minus VT whole square by 2. So LCM will find out 2 VGS minus VT whole square minus VGS minus VT whole square by 2. Then we'll get VGS minus VT whole square by 2. So finally I'm writing the equation. VGS minus VT whole square by 2 whole square by 2. So this is seventh equation will become this one. So what is the equation number? It is 11th equation. Equation number 11. Now IDS of this in gate to channel capacitance. So we can substitute in the place of VDS, VGS minus VT. VDS, VGS minus VT. Now the IDS is equal to CG into mu by L square. Then substitution will get VGS minus VT whole square by 2. Whole square by 2. This is the equation number 12. Equation number 12. Now the final equation, capacitance per unit area. Capacitance per unit area, the IDS equation will, IDS is equal to C0 into mu W by L VGS minus VT whole square by 2. Whole square by 2. So this is a last equation, capacitance per unit area. 13th equation you can see. So this one, C0 into capacitance per unit area, CG is equal to C0 W into L. So then this equation number 9 will become C0 W by L, W by L into mu. Now in saturation region you can substitute this, rewriting the equation number 10, rewriting the equation number 9. Rewriting the equation number 10 will become VGS minus VT into VGS minus VT minus VGS minus VT whole square by 2. Simplification, VGS minus VT whole square by 2. Now this is 3 equations of saturation region which are written in non-saturation region. So this is a current equation IDS and VDS in saturation and non-saturation. Please subscribe the channel, like and subscribe to inform to your friends. Let us share this one. Thank you.